As you learned in Module 2, Polya's problem-solving method is not just applicable to mathematical problems, but to almost any kind of problem. We'll look at a logic game, a non-mathematical problem, and illustrate Polya's problem-solving method. Recall the 4 steps of Polya's problem-solving process: understand, strategize, solve, and look back. Some aspects of this, like most of the math skills you learn in this course, to solve problems, are familiar to you. However, other skills, such as truly understanding and defining a problem, looking back to evaluate the problem and understand it in a greater context, and strategizing on how to solve the problem, may be less familiar. In this logic game, we'll be looking at a completely non-computational issue, and we'll be focusing on the strategize portion of the solution, as well as looking back and understanding the greater context. Let's consider a problem now. Imagine that you are the assistant coach of a crew or rowing team. 7 members of the team, Eric, Fred, George, Harold, Ian, Jacob, and Kevin, are being assigned positions on their boat. 1 position is in the front of the boat, and 3 are on the port side, while another 3 are on the starboard side. The head coach states that the following conditions must apply. Harold is placed on the same side as Kevin. Fred is not on the same side as George. If Ian is placed in a port position, then Jacob is in a starboard position, and Fred and Jacob are placed in starboard positions. The first step of the problem-solving process is to understand or identify opportunities for problem-solving using mathematics. Here you have a number of conditions provided by the team's coach, and you want to see if you can satisfy a particular rower's request. The objective is to apply the constraints that you were given to determine whether you can realistically satisfy this request. Let's look at what we know. You have 7 team members. You have 3 categories with 1, 3, and 3 elements in them respectively, and you have 4 very straightforward constraints. So the info you were provided gives you the overall configuration of the situation, all of the elements in the situation, and those 4 constraints. Remember, you have those 4 very straightforward constraints, but you don't necessarily know how they work together to further specify the situation. So you expect that this will be a part of your strategy. Fortunately, strategizing is the next step, which involves selecting an appropriate technique for addressing the problem. We have lots of dispersed information here, and we're not sure how it connects, so the best strategy is to begin with a diagram. We have 7 possible slots in 3 categories, so we'll draw a 3-column diagram with a front column having 1 row and port and starboard columns having 3 rows. We also have numerous constraints that need to be related, so we'll fill in the diagram as much as possible, given the constraints. Let's follow this strategy now. Solving is the phase in which we follow the strategy. We'll apply the appropriate mathematical techniques, in this case logical reasoning, and leverage appropriate technology tools to come to a solution. We have 7 possible slots in 3 categories. So here's our diagram. Remember that we had 1 slot in the front of the boat and 3 slots in each of the port and starboard sides. So our columns correspond to the people or positions in the front, port, and starboard sides, and the rows correspond to the number of available slots. We'll begin going through each of the constraints now and place information in the slots as we know that information. Let's look at our first constraint. First, in order to make things simpler, we'll abbreviate the players' names: E, F, G, H, I, J, and K. Our first statement is that Harold is placed on the same side of the boat as Kevin. We don't know exactly how to put this into the diagram yet, so we'll denote it off to the side, H and K together in 1 box. However, we do know that because Harold and Kevin need to be on the same side, they can't be in the front of the boat. So the only possibilities for the front are E, F, G, I, and J, and we'll denote that here. Our next constraint is that Fred is not on the same side of the boat as George. We don't, again, know where Fred or George is in the boat right now, so we'll make another note on the side. If Fred, then, which we'll denote with an arrow, no George. Our next constraint is that if Ian is placed in the port position, then Jacob is in a starboard position. Again, we don't know where Ian is placed, so we can't really say anything about Jacob here, so we'll write this over on the right-hand side again. If Ian port, then, again an arrow symbol, no Jacob on the starboard side. And finally, Fred and Jacob are placed in starboard positions. Aha, finally something we can put into the diagram. So we'll put Fred in one starboard position and Jacob in another starboard position. We also know that Fred and Jacob can no longer be in the front position, so our options for the front position have been reduced to E, G, and I. Now we look back at our constraints over to the right to see if we can fill anything else in, and indeed we can. We know that Harold and Kevin have to be together. They can't be in the front, and since there's only one position left in the starboard position, we know that Harold and Kevin have to be on the port side. Now we'll look at another constraint. Remember that we know that if Ian is on the port side, Jacob is not on the starboard side. Since Jacob is on the starboard side, we know that Ian can't be in the port side, so the only options for the port side are E and G. Finally, we have if Fred, then no George, meaning that wherever Fred is, George cannot be. So the only options for the starboard side are E and I. Now let's go back to our question. We've determined as much as we possibly can about the positions of each of the members of the crew team in the boat. Remember that we were asked whether Eric and George can be placed together on the same side of the boat. Well, we know that Eric and George cannot be in the front of the boat because there's only one position there. And in fact, there's only one position left in the port and the starboard side, and none of the occupied positions belong definitively to either Eric or George. Thus, Eric and George certainly cannot be placed together. They have to be placed on different sides of the boat. So, we've answered our question. Now that we've solved our problem, it's time to look back. This involves interpreting and communicating the information that we've just discovered. In this case, the information is somewhat quantitative, but not directly, so we'll call this qualitative information. The first step then is to check whether our logic is correct. We didn't do any actual math. And also whether we answered the question we were asked. If we were to recheck, we would realize that the logic is in fact correct here. Let's just take that as a given in this case so that we don't have to do the problem again. We also answered the question we were asked, whether Eric and George could be together. We determined that they cannot be together on the same side of the boat. Now let's interpret. What do we know, and how does this relate to a greater context? We know a lot about the constraints of the problem. We realize, in fact, that there are only two possible configurations. Look again. If we know who is in the front of the boat, for example, say it's Eric, we then know who's in the port side of the boat. It must be George. And who's on the starboard side? It must be Ian. Similarly, if we know that George is in the front of the boat, we know that Eric must be on the port side. And since Eric is on the port side, then Ian must be on the starboard side. Finally, if Ian is in the front of the boat, we know that Eric must be on the starboard side, and thus George must be on the port side. The same would be true if we determined who is in the port or the starboard side. In fact, there are only three possible configurations. And finally, we communicate. To whom would we communicate this information, and how? We may have to communicate this information to any of the players. For example, a good starting point would be Eric and George, because we won't be able to accommodate the request. The best way to communicate this would be to give verbal communication, explaining our rationale, as well as showing the constraint diagram here. If we were to show the limited number of possibilities, people would better understand how the constraints play into everyday life. This is a great case in which we build a diagram, and that diagram can be directly used to accomplish our goal. In summary, Polya's problem-solving method, understand, strategize, solve, and look back, can be used in a variety of non-mathematical contexts as we've seen here. It's hugely powerful.